Yeah, thanks, Michael. My talk is actually FEM for fractional diffusion, pretty general. And I would say this is joint work of our student Björn Bahr and Jens Markus Melling and Dirk Portoris, all from TU Wien. Okay, let's jump in, give you a motivation why you should do fractional and state the main results. So why fractional powers of differential operators? I mean, in general, think about you have a random walk where you're at this position and you jump either one step forward or one step backward. Okay, then this governs the Brownian motion. And if you take the limiting process, the corresponding differential equation would be the heat equation. This is well known. But why restrict yourself to jumping one step in front or one step in back? Maybe you jump 8 meters. Okay, it's highly unlikely that I can jump 8 meters, but yeah. So long jumps might be possible, but have low probability. So if you write down some probability distribution for that, this would govern your Levi process, and the corresponding differential equation would then be a so-called fractional heat equation. So there, this would appear naturally. And yeah, if you only think about modeling physical processes, this would allow you to give you an additional parameter for your models. So, and this is used in non-local physics, image processing, finance, material sciences, and really in industry. So somebody asked me to do this for a loudspeaker. And there are, from a mathematical standpoint, there, as Tobias already said, there are non-local effects. This is pretty challenging, but this makes it interesting. And yeah, it's an active research field. It's always nice to have people maybe interested in your work. Okay, so let's look at a fractional PDE. And I will write down what this means in 5 minutes. But sorry, some things. Okay, but the general thing about fractional PDEs is they become singular near the boundary. And think about here, I've plotted a solution on an L shape, and you can see very steep decay at the boundary of the L shape, or zooming into to a corner. You can see some singular behavior there. And different to general PDEs, non-fractional PDEs, you will get singular behavior at the whole boundary. So solutions behave like a distance function of some point to the boundary to the fractional power on the whole boundary, close to the whole boundary. So in general, you will expect, so this is not a smooth function here. So you would expect singular behavior near the boundary, so reduced FEM convergence rates, obviously. So solution, as I'm here, as you all know, can be adaptivity. And so you refine your mesh towards the singularity, and this is how a mesh for a fractional PDE would look like in 2D. So really a lot of elements very close to the whole boundary. And the first part of my talk, I want to actually explain you, if you do uniform refinement, you see this rate, and if you do adaptive refinement, you see this rate. So this will be the optimal convergence of FEM. And in the second part, I will actually tell you that, yeah, there are some computational difficulties arising, how you can treat them. In a sense, how do can you make your FEM more efficient? Okay, yeah, this is the 2 parts. And so we'll right jump in. So what's the mathematical formulation of our problem? So how is even, I don't know if everybody's familiar with fractional PDEs. So how is this operator even defined for a parameter in 0, 1? Well, there are many different possibilities. The easiest one you can think about is Fourier transform. Okay, the Laplacian has a Fourier symbol theta to the power 2. Okay, if I want to have something which is a little bit smaller, just multiply with s here. Okay, and taking the inverse Fourier transform to define the operator. Okay, this would be the standard Fourier transform definition. Obviously, we won't do numerical analysis with that. But yeah, you can define it in this way. But there are many more. And there is a nice work by Kwasniczy, which is named 10 equivalent definitions of the fractional Laplacian. So this is the main work on these definitions. We're using the so-called integral fractional Laplacian, which is defined as a singular integral. So it's pointwise defined as a Cauchy principal value up to some constant of the function u of x minus u of y divided by some integral kernel. And you can see this fractional power enters here in the singularity at the kernel function. Okay, and yeah, as I said, there are many more. For example, you can use the spectral theorem, produces your so-called spectral fractional Laplacian. You can use semi-group theory, or define it as a Dirichlet Norman operator for a degenerate elliptic PDE. We will come to that later on. And this goes back to Caffarelli and Silvestre. It's a very, very influential, in my opinion, because you can take PDE techniques there. Okay, and as I said, it's named 10 equivalent definitions. So they are all equivalent on RD. So maybe I should mention, this is an integral over all of RD. So if you look at the full space, then they are all equivalent. If you restrict yourself to a computational domain omega, they are not equivalent. So you have to pick one, and we picked the one, this one. So we take this formula here, only for x in omega, and write down an exterior boundary condition. Okay, so this is our function setting. And yeah, standard Hilbert space is HS tilde. So global HS are functions which vanish outside. And with that, yeah, we can write down the weak formulation. This is all completely standard. So in a symmetric way, this is your bilinear form, U and V, okay? And answers and test space is HS tilde. Galerkin formulation, just so the space of piecewise polynomials of degree 1 is a subspace of HS tilde with zero boundary conditions. So we can just replace all these quantities by the discrete functions and have your Galerkin formulation. And by Lax-Milgram, the Lax-Milgram lemma guarantees unique solvability of the Galerkin formulation. So this is nothing new. What about optimal adaptivity? So this is again nothing new. This is the standard adaptive loop. So going back to Dörfler in this 1996 paper in this way. So we iterate with an initial mesh, we iterate the solve, estimate, mark, refine loop. So we solve on the current mesh, produce you a discrete solution, compute some indicators, then mark a percentage of these indicators with so-called Dörfler marking, and refine at least all the marked elements. Doing NVB guarantee you some quantities of meshes like no hanging nodes and so on. So I won't talk about mark and refine. These are completely standard. So I will talk a little bit about solve and a lot about estimate. Okay, so because these are the things you need to do for your model problem. Okay, so what about solve? The model solve can be done iteratively if you want. But again, this suffers from a little bit of a drawback in the sense that if you have your stiffness matrix, the condition number will get worse if you do adaptive refinement. It will grow anyhow with n to the power where this fractional power comes in, but it will also produce a factor of maximal divided by minimal mesh width. And if you look at my picture before, I only refined towards the boundary, so this will get very, very big. Okay, you can say just do diagonal scaling, this goes away. Yeah, you can do that. Or if you do any preconditioning anyhow, I suggest you do, I mean, there are many more things. For example, the operator preconditioning, which Rob Stevenson did in his group, or you can do a local multi-level diagonal scaling. So I said this is just an additive Schwarz preconditioner. You can do this for a problem. And we actually should, so for non-local problems, this was done for the boundary element method by Feischl-Führer, Petor, Stefan. And we actually showed for the fractional Laplacian that if you do this additive Schwarz preconditioner, you can bound the condition number of the preconditioned system by a constant, which might depend on this fractional power, but not on any crucial thing of the problem like mesh width, degrees of freedom, or any. So you get a bounded condition number. In this sense, you can solve iteratively with our preconditioner very well. And this preconditioner can be cheaply computed. This is the module solved is essentially solved. And one more thing, Riccardo Androchetto and his co-workers actually improved on our bound by replacing, he did some trick on the causes space in this multi-level decomposition to actually get rid of this S dependence. Okay, so to show you the performance of our preconditioner, so this would be an adaptive refinement for in 2D for parameter 0.25 on the L-shaped domain. You can see, okay, the non-preconditioned system has a condition number which grows pretty fast, and our condition number actually is essentially bounded by n. You can do better with other preconditioners to reduce this 10, but in my opinion, 10 is fine. Yeah. Okay, so this was the model solved. What about the model estimate? This is actually something where a lot of work has to be done now. So which error indicator do we want to take for the fractional Laplacian? You can just say, well, take a residual indicator. Yeah, you can do that. Usually you have to measure the residual, so plug the discrete solution into your equation, measure the residual in the dual norm. This would be an H minus S norm. Yeah. Not that nice, so not that localizable as we learned before, maybe. So I don't know how to localize it. So we just say, okay, we take a weighted L2 norm instead. So multiply with the correct power, which will be power S, and take local L2 norms. So the L2 norm is localized, so I can actually compute local indicators. Okay, these are the local indicators. Yeah, nice idea. It's not our idea. Goes back to, I don't know, lots of years. But for fractional, the idea, so the Einzel and Gluser and Ricardo Noschetta and his group actually proposed this error indicator. And yeah, they can show that this is a reliable error indicator, summing up all these quantities squared and taking the square root is an upper bound for the error. But now comes the big but. Now adaptivity is not finished. Why? This quantity is not well defined. Now, in our case, it may not be well defined. Why? Well, fractional Laplacian makes a regularity shift of 2s. So if you have the classical Laplacian, you take an HT function, you would get an HT minus 2 function. For a fractional, you get an AT minus 2s function. Okay? And we plug in a discrete function here. So a discrete function is in the Pisos polynomial space P1, but this is a subspace of H3 half minus epsilon for any epsilon, but not more. So if you make this regularity shift of 2s here, you might get a function which is not in L2. So for example, if you take the fraction parameter bigger equal to 3/4, this will not hold. So it's not an L2 on each element either. So what's written here and proposed here and here is not well defined for all fractional parameters. And yeah, obviously Ricardo Noschetta noticed this and proposed some error indicators by leaving the L2 setting. And he was able to go up to 9/10 or something like that. But still there was a small gap there. And you leave the L2 setting, which you might not want to do, maybe. Okay, so our idea was, maybe you can improve on that. And the thing is, what goes wrong? What goes wrong if I plug in a discrete function into the operator? Well, you have some, inside each element, you have some blow up. And this blow up can be measured. It can be measured by taking one point and looking at the distance to the skeleton of the mesh. So this gives you a so-called, I call it a local distance function. The local distance of a point to the mesh skeleton. And what we were able to prove is, if we take a sufficiently large power of this distance function and multiply the fraction Laplacian of this discrete function with this local weight function, we get something in L2. So we actually scale away this singularity on the mesh skeleton. Yeah, and the idea is, okay, now once we have this lemma available, okay, just replace the thing which was bad before by the thing we can actually control. Okay, so for bigger fractional, so for s smaller than 1/2, you don't have to do anything there. You can take the standard estimator. So for s bigger than 1/2, for example, you can choose this parameter to be s minus 1/2 and define a modified estimator where we just modify this h weight. We modify the h weight. We take, instead of writing hl to the s, we write hl to the s minus beta. And this minus beta will be done on the beta of the local weight function. So you can always bound this local mesh width, local distance function by the local mesh width. So this is actually something smaller than the classical residual area indicator, which you have to do because the other one would be infinity for the case. So this is something which is, I call it the modified area estimator, which is lower than the classical residual area estimator, but we can still show that it's, at first, it's well defined by this lemma. And the second, we still have reliability. It's still an upper bound for the error. Okay, so we can use this to actually do our adaptive algorithm. Okay, and then can say, what about, did we lose something? Unfortunately, no. So we're still able to prove the following theorem. And I would say this is, we call it the main theorem on age-adaptive algorithms. And the formulation of such theorems go back to Stevenson in 2017. And yeah, we have to mention the work by Carstensen, Feischl, Pache, Pretorius called Axioms of Adaptivity. And this is actually how we formulate our theorem based on this work here. Okay, so the idea is, if I do n steps in my algorithm, we can show that our modified error indicator contracts with q to the n, so linear convergence of the error indicator. Okay, and the second statement is, okay, let's take all possible refinements of the initial triangulation of n elements, take an arbitrary parameter r, and assume something on the marking, so that the marking parameter in the Dörfler marking is sufficiently small and you don't mark too many elements. There's a talk today which addresses this issue, so I'm very interested in this talk by Kreuzer. But we have to assume that the marking parameter is sufficiently small. Okay, and then we can show that the following statement. Okay, the statement here tells me that the number of elements in my adaptive mesh to some power r and multiplied with the error indicators is equivalent to this quantity. What is this quantity? This tells you that if I take the optimal mesh and the optimal error indicator on this mesh, if this decays with rate n to the minus r, actually also my adaptive algorithm reproduces this rate. So this tells me that if rate r is possible, the FEM steered by this error indicator produces this rate. And this explains this picture. For uniform refinement, nothing better than in our problem n to the minus 1 over 4 is possible. But for adaptive, we get n to the power minus 1/2 or O of h. Okay, so if the problem allows for the rate n to the minus r, FEM reproduces the rate. This is the theorem. How to prove that? Well, fortunately, in this Carstensen, Feischl, Pache, Pretorius work, there's a lot of work done for us. So the idea, this work is called Axioms of Adaptivity. So they proposed to only show 4 quantities of the error indicators. So just look at the error indicators, prove 4 things, and you're done. You don't have to do anything about, yeah, the rest follows if you do NVB, let's say that. Okay, so what do you have to do? 4 properties of the error indicator guarantee the linear convergence and the optimal algebraic behavior. So just a statement, A1 is called stability, A2 is called reduction, A3 is called discrete reliability, A4 quasi-orthogonality. I will come to the details. I would say the beauty of this work is that the model problem and discretization only enter through the proof of the axioms. So you only have to do this for your model problem, but not the rest. So it works for FEM, it works for PEM, and as I tell you, it works for fractional. Okay, so A1 is actually the crucial thing for fractional. The rest is pretty much standard. So what is A1, so-called stability? So you take any possible refinement of your initial triangulation and a subset of the elements, and you take 2 different discrete functions on this mesh. And this tells me, so if I look at error indicators summed over the subset, where I plug in the function VL and the function WL, the difference of the error indicators can be bounded by the difference in the energy norm. In this sense, this is Lipschitz continuity of the error indicators in the energy norm. Okay, so this is one crucial property. So how can we show that for our fractional problem? Yeah, well, this is nothing else than a definition of the, so this is the definition of these quantities here, or upper bounds of this, whatever. So this was our modified error indicators. So we use the triangle inequality. Triangle inequality gets rid of these F terms. So you have this guy here. And now you ask with the, can I bound this guy directly by the energy norm? If I can, I'm done. Okay, but this is not clear how to do, because this is actually an inverse estimate. And this is what the main part of our work was, to prove this inverse estimate. Okay, and actually, so we need a local inverse operator on locally refined meshes. A lot of local in there, so it's not trivial to do this, in my opinion. I don't know. And as usual for an inverse estimate, you bound a stronger norm by a weaker norm. So this only works in a finite dimensional setting. But fortunately, we can plug in a finite dimensional function here. But it's not trivial because you apply the operator to it. So it follows not directly from properties of polynomial spaces. Okay, so yeah, this was the crucial lemma here. So showing this inverse estimate. And the constant here is, as it's needed, independent of the measured function and crucial quantities. Only just some things like shape regularity go in there. Okay, so how can we prove such an inverse estimate? Well, at first we use locality of the L2 norm. Sum it up in local contributions. And then, okay, now we go into the problem that the fractional Laplacian is non-local. So the operator is non-local. I cannot do anything localization for this here. But as I say, if it's not local, make it local. So the remedy of this is we just split the operator. Split the operator in a local part and a non-local part. But this non-local part will be something more regular. So I would say this is the general idea I will use twice today, is split it into something local, something smooth. So more general, so what do I take here? So I take here some kind of a cutoff function, which is supported on the patch of the fixed element. So I have an element fixed here, take the patch of the element, take a cutoff function supported in there. And yeah, for Poincare purposes, I also take a constant in there. So this is the localization, but it's inside the operator. This is the crucial key. Okay, and yeah, this is just the remainder term. I call this near field and far field. Let's look at the near field. Obviously, I won't be able to prove the whole estimate, but I will give you the idea how to estimate. So the near field is actually localized because the localization is inside the operator. Okay, so I can estimate it by using mapping properties of the operator. Then I get something like an H2S norm. So since this is shifts of 2S, I get a 2S norm of this localized quantity. Okay, still the norm is non-local. Okay, but thanks to this Faustmann work of 2000, there's a localized upper bound for this. So even though the norm is non-local, I can again use something localized as an upper bound. Okay, so I can localize this and then use Poincare inequalities on patches. But still there is some, you have some, so this guy here actually lives on T, but you also have elements which are not T so far away. But if elements are separated, you can also use that such quantities for X and Y separated are actually smooth. This goes into the proof. Okay, so not more on the near field. What about the far field? I said the far field will be something smoother. So actually, we had one element, and think about the fractional Laplacian. We said something like X minus Y. So if X and Y are separated, you get something smooth. Okay, so this will be the main idea behind that. But in order to give an estimate for the far field, we actually used a different interpretation for the fractional Laplacian. The different interpretation was by using, as I already said, this Caffarelli-Silvestre extension problem. So this is applying PDE techniques to the problem in the sense that if you have a function which solves this problem, so this is I add one variable, and this is a degenerate elliptic problem. So in this new variable, I have this weight function here. This weight can go to 0 if y goes to 0, or to infinity if this alpha is negative. So this is a degenerate elliptic problem, and if I have some Dirichlet boundary condition on the y equal to 0 boundary, then, so if this power is correct, then the fractional Laplacian can be recovered as Neumann data of this extension problem. So the Neumann data of this problem is nothing else than the fractional Laplacian applied to the Dirichlet data. In this sense, this is the Dirichlet to Neumann operator for this degenerate elliptic problem. And the key is, okay, using some trace inequalities together with stuff for this PDE, I can actually get estimates for the fractional Laplacian. And this is now a local problem. This is a PDE. There's no integral operator involved. Okay, and since this is a more or less elliptic, so degenerate elliptic PDE, you get some interior regularity results. This is actually what makes the actually uses the smoothness of the far field by employing interior regularity. A so-called Kachople inequality. So you take some weighted L2 norm, weighted with this correct weight here, and you take two sets. So let's say a set B, it doesn't have to be a ball, and a set B star, B prime, sorry, and they are nested. It should not touch. This should not touch the boundary of the other. This is the only thing we require. And then we also require that the Dirichlet data here and the larger set here, they have to be separated. This is what can be done for the far field, because for the far field we actually cut out so we subtracted this localization of the near field. So what you plug into the operator here is 0 somewhere, and the 0 somewhere will be exploited by choosing the correct B prime. In this sense, for our setting, this Kachople inequality can be applied, and the statement tells me that okay, if I take the second order derivatives in X, for example, in this weighted L2 norm, I can bound them by the first order. So classical interior regularity for this extension problem. But we use that actually the data and the data is localized away from this larger set I'm looking here. This makes everything go. So with this, I exploit this additional smoothness for the far field. Okay. So this is all about this inverse estimate. So I hopefully have convinced you that A1 holds. What about the other properties of the error estimator? Well, they follow with standard techniques. It's a modified estimator, so you have to do them again somehow. But they are nothing deep, nothing new, I would say. So reductions again means that the error indicator on refined elements can be bounded by a constant smaller than 1 on the elements, on the non-refined elements. Okay, this is a property of bisection, I would say. Discrete reliability means the difference between two discrete solutions can be bounded by the error indicators on the common elements. Okay, this follows from Galerkin orthogonality, some properties of the Scott-Zhang projection. Okay, there you need Scott-Zhang projection in these non-local norms, but this works. And a scaling argument to actually get here the correct local distance function in there. But nothing too deep. And finally, quasi-orthogonality. Just think about Galerkin orthogonality. Follows from ellipticity in symmetry. Okay, so let's jump into some numerical results. So 2D unit circle, you can see, okay, strong refinement towards the boundary. If you take a suitable constant, you can show that the solution actually looks like this, which is nothing else than the distance to the boundary to the power of S. Okay, what can we see on rates? So S 0.25, you get a rate for the estimator and for the error of n to the minus 1 over 4. It's what you expected before. And for the estimator and for the error, with adaptive refinement, you get double the rate. Same holds true for larger S. Okay. Second example, let's take a discontinuous right-hand side. So for a discontinuous right-hand side, which is nothing else than the characteristic function in polar coordinates of the right part of the circle, then a mesh may look like something like this. So you're not only refining on the boundary, but you're also refining this discontinuity of the right-hand side automatically in your algorithm. Okay, and same goes for the rates. So again, n to the power -1/4 for uniform refinement, and to the -1/2 for adaptive refinement, both for both fractional parameters. Okay, I'm good in time. So yeah, I just said, okay, we can compute these error indicators. Yeah, we can, but there are some computational difficulties. Let me sum them up here. So we actually need to compute the L2 norm of the operator applied to a discrete function. This might get singular. So in order to compute this L2 norm, we need to have some kind of an accurate quadrature for each element. So actually, in order to make this, to be on the safe side, use HP quadrature. This is expensive. And the second thing is, I need to evaluate the operator in order to evaluate the residual in the quadrature points. Okay, how to do that? Well, for example, you can use this formula here. Looks a little bit messy. Think about x being a quadrature point. Then if this is inside one element and you have a piecewise linear function, this is nothing else than an integration by parts formula. So in this sense, you write this kernel as a gradient and do integration by parts. And then you would not have integrals over t, but only over the boundary of this element. But here comes the big but. I mean, these are, for example, in 2D, these are 1D integrals. They can be realized quite easily with quadrature. But you have a sum over all elements of the triangulation, as the operator here was defined as an integral over RD. Okay, RD, and then you cut it off somewhere, okay? But you still have all elements in your triangulation there. So evaluating here at one quadrature point, you need to have at least an O of n algorithm here in each quadrature point for each element. Listen, in total, an O of n squared algorithm multiplied with the constant here might be big due to the need of accurate quadrature. And yeah, in 2D, you really see that the computation for the error estimator is really, really slow. How to improve on that? You can say, yeah, throw away the error indicator. This is bad. Yeah, you can do that. You can, for example, think about a two-level error estimator, and this is something we do right now, do with Ernst Stefan and a student of us. But the drawback of the two-level error estimator is you can only show optimality under a saturation assumption, which you will not be able to prove. So this is, in this sense, the drawback there. So here we can, without saturation assumption, we have optimality. But stick back to the modified residual error indicators. So if idea works once, do it twice. Do it as long as it doesn't work. So the idea is, okay, maybe I don't need the accurate quadrature everywhere, and I don't need this sum over all elements everywhere. If I decompose my error indicator into something which is localized somewhere and smooth somewhere else. So I split it into two parts again, into a near field part and a far field part, but this time the error indicator, not only the operator. Okay, and the idea for the near field part this time is this will be treated explicitly. So we will write down an upper bound for this, which can be computed without quadrature. So we modify the error indicator in this sense again. And the far field part is actually, again, smooth. So we can use cheap quadrature there and even use fast computation techniques such as panel clustering, H matrices, fast multiple, whatever you want. So what is the idea? Again, well, we take a point X, think a quadrature point, take element inside there and cut out a ball around this element. Okay, this is done with such a cutoff function, and define the near field again as the operator where we cut out this ball. Okay, and the far field is just a remainder operator. Okay, so as we have cut out this ball, we have something local again, but we have even something better if you want. If you define the maximal gradient jumps on this ball we cut out, so the gradient of a discrete function is a constant. So inside this ball we cut out, we have a lot of different constants. And if you define the maximal jump of all these constants, so this is the maximum gradient jumps, inside this ball, we can actually directly bound the L2 norm of the near field on one element by this maximal gradient jumps and the correct power of h. And the idea is now, instead of computing a quadrature here for the local part, but which includes the singularity, we just compute this upper bound here, which is just jumps of constants and h power. So instead of using this thing, we use this thing to steer our adaptivity, at least for the near field part. We use the upper bound for our computation. And this is computed super cheaply. There's no quadrature, no evaluation needed. Okay, try this. What about the far field? So the second part where the remainder where we have cut out everything, has a kernel which looks like this. This is for people who worked in compression techniques. This is obviously that if x and y are separated, suitably separated, you can, for example, write down a separable expansion for this. So you can, for example, use Lagrange interpolation, write this kernel as evaluated at interpolation points and Lagrangian polynomials. So you separate the variables and plug this back into your operator. Plugging this back into your operator here tells you that, okay, I have these y integrals, and here's some multiplied with some functions of x. And if you want to compute the area indicates later on, there will be an integration over x on the outside. But the crucial quantity is these y integrations here, they can be computed once for every quadrature point in x. In this sense, you will gain your computational effort there. Standard techniques applied to H matrices, for example. But they can be applied here once we do the splitting, and we have to do it anyhow to get rid of this singularity for the near field part. So we get this for free here, if you want. Okay, so then computing the whole L2 norm of the far field can be done now with element-wise Gaussian quadrature. No need for HP quadrature because we have cut out the singularity already. Yeah, so, this numerical approximation, I said, okay, if x and y are suitably separated, yeah, just do a hierarchical partition of your, so collect all the interpolation points, collect all the quadrature points, cluster them together, do a hierarchical partition, like in a panel clustering, and you get, with standard admissibility conditions, you, for example, get an O of n log n algorithm for your total complexity for the computation of the far field and the near field together. And yeah, does this work? Yes, it works. This is a 1D implementation of our student. He just works on 2D right now. Taking the right-hand side as the signum of x. So we take the interval -1, 1 in 1D. Then the exact energy in 1D can be computed. Yeah. And what can you see here? You can see here this modified estimator, where we actually used H matrices, also this fast techniques for the far field, and replaced the near field just by computing this upper bound of the gradient jumps. You can see, yeah, this produces you the rate n to the 2 minus s. This is the optimal rate in 1D. So in 1D you get a better rate. Now for sure somebody will ask afterwards, why don't you see this rate in 2D? Well, in 2D you would need anisotropic refinement to really produce the optimal rate for a fractional Laplacian. But in 1D you don't need any isotropic refinement to just have one direction. So in 1D, you will get the rate n to the 2 minus s as best possible rate in the energy norm. So the energy norm is the HS norm. We work with piecewise linear polynomials, so you can expect up to H2 regularity, you get 2 minus s as a rate in 1D. In 2D, this is an open question to prove with anisotropic element. Okay. So this is the error. So you can see that actually our modification of the error indicator does not ruin the optimal convergence, which we have not proved yet. And this is now the computational time. So this would be the standard estimator, so the standard weighted residual estimator. This is an O of n algorithm. And you can see here, this is the modification with it. It's really an n log n algorithm in computational time. Okay, and so with this, I will conclude. As what did I show you? I show you that, okay, you can do FEM for fractional, which has boundary singularities, and yeah, doing it with our novel residual type area indicator which works for all fractional parameters, you can get an optimal convergent algorithm. And the second is, yeah, we can actually write down an upper bound for our estimator, which can be efficiently computed, which in numerical experiments don't ruin the optimal convergence and has an O of n log n realization. Okay, so what's ongoing work is a quadrature analysis for this modified estimator. And for example, looking at other fractional operators for the spectral fractional Laplacian, you can also do adaptivity. There can also be some stuff done there. And as I said, look at different error indicators like the Twolevel error estimator. Okay, so if you're interested in our work, so this optimal convergence work is already published in MathComp and available in arXiv. And the second thing, this efficient realization will hopefully be done somewhere soon. So that's work in progress. Thanks.